Hey everyone, so I want to move on to the next topic. So we just finished talking about rotational kinematics, and just like in the units that we did when we started with kinematics, the next thing to talk about is forces and dynamics. So we're moving on to statics and torques. Like I said, we're kind of redoing the entire unit, but in the rotational sense, right? So we've already talked about the forces acting on an object and what it means to be in equilibrium, right? And we know that when the sum of the forces equals zero, the object's in equilibrium. However, in that specific case, what we're actually talking about is what's called translational equilibrium. Just like before, it's the idea that the object isn't moving left, right, up, down, or anything like that. So let's consider this case. Imagine we have a seesaw. We place a 1 kilogram object here and a 1 kilogram object here. Now, translationally, this object would be in equilibrium, right? We have a 10 newton object pulling down here. We have another 10 newton object over here. And this pivot will actually ex- uh, give a force that's 20 newtons going up, to kind of balance everything out. So translationally, this system would be in equilibrium. But is it actually in equilibrium? Is it going to remain at rest if I let this system go? No, we know that this side is going to end up tipping over and this side's going to go up. So it's not in complete equilibrium because there's something else going on rotationally that is going to cause this object to rotationally move, even though it's translationally not going to move. So this is going to end up having us now need to discuss the concept of rotational equilibrium to bring it in. And in this case, now when we say an object is in true equilibrium, it usually is going to mean that both rotationally and translationally it is in equilibrium. Um, so when we say that the rotational equilibrium, it means that the object's not going to rotate clockwise or counterclockwise, or it's going to do that at constant speed. I just want to point this out that at this point, if I only say that the object doesn't rotate, keep in mind that that also means that it rotates at a constant speed. It's going to be interchangeable. What I mean is that its rotation isn't changing. That keep that in mind. Just because it kind of gets a mouthful to constantly say that it's not rotating and also or could be rotating at constant speed. So just keep that in mind that this is kind of going to be inherently always included. Right? Now, how will we know if an object's in rotational equilibrium? What we have to do in the cases of forces, our translational concept, we looked at the forces to see if the net force is equal to zero. So now what we have to do is talk about the torques. We're going to say that if an object is in rotational equilibrium, then that means that the net torque is equal to zero. I want to remind you again that one of the things I've said before about the way to kind of grasp this topic a lot easier is to constantly relate back to what we've learned before and replace the linear terms with angular terms and vice versa. Keep that in mind because nothing has really changed. All I did was replace the word force with torque, and the concept still stays the same, right? So the sum of the torques acting on an object or on a system is going to be equal to zero if the object's in rotational equilibrium. So we kind of mentioned torque, I think, very briefly in the previous in class at some point. You've probably heard it before. So what is a torque? A torque is just any force that causes an object to rotate. That's all it is. So it's the idea that you apply a force on an object and then that object starts to rotate. All of a sudden, that force is now providing a torque. Now, you can apply a force on an object and cause it to move without causing it to rotate. So it's not necessarily that the force can only be a force or a torque. It just means more that the force can cause and can act as a torque on an object. Right? Um, and how do we end up getting this torque effect? Well, in order for you to actually cause an object to rotate, you have to apply a force at some distance from wherever the object is going to pivot. So, for example, if you have a door and you try to apply a force onto the hinge, that object is not going to rotate. It doesn't rotate from that around that pivot point. You might cause it to move, translationally, but it won't actually rotate. So that's why you have to have your force applied on the other side, away from the hinge, in order to open up the door. And then once you apply that force, then the door will actually rotate. Therefore, your force will act as a torque to cause it to rotate. Uh, there are three factors that you need in order for you to find the torque acting on an object. First is how far away you are from the pivot. You also need to know how much force you're applying, and the angle of the force does matter. Uh, I'll try to show this in class because it is extremely important, but the way you apply your force matters and will change how much torque is acting on the object. The torque is the greatest when the force is perpendicular to the object. Again, you can kind of see this yourself if you go and push on your door. You can see that if you push on it, perpendicularly, the door will rotate very easily. But if you try to push at any sort of angle, either away from the hinge or towards the hinge, you'll find that in order to rotate it the same amount, it's going to require a lot more force on your end. So the equation that we have for torque is this. Torque, which is this symbol is a tau symbol. So tau equals RF, where these two terms are perpendicular to each other. Or we could write it as RF sine theta, where this angle, theta, is the angle of your force relative to the pivot arm, right? So unfortunately, I can't actually draw on this, so I'll try and show this in class later on. But the key thing for now, at least, is just to be able to use these equations. So the R term and the F term have to be perpendicular to find this torque. And if the force is acting at an angle, then you just have to plug in what that angle is. Right? Um, Yeah, so like I said, for the most part, torques end up working very similar to forces. It's that same idea. One thing to keep in mind is we need to define the positive negative direction because torque is a vector. So we're going to define clockwise as positive and counterclockwise as negative. Now I know I had mentioned in class that conventionally it's the other way around. Again, doesn't really matter. As long as you're being consistent, that's really all that matters. So a lot of times what you have to do is when you are looking at the forces acting on an object, you kind of want to ask yourself is what direction is this going to rotate? Is this going to cause the object to rotate clockwise or it's going to rotate counterclockwise? The really nice thing is that you have a perfect item at your disposal at all times to actually see this yourself, and it's your pencil. What you can do is, if you're trying to think about what direction the object's going to rotate based off the direction of the force, you can take your pencil, put your finger at the point that would represent where the object is rotating, and then apply the force in that direction, and then you'll see your pencil rotate, and you can tell yourself, okay, it's rotating clockwise, or oh, it's going to rotate counterclockwise. So that's the way that you can actually physically see it yourself if you're having trouble visually understanding what's going on. Right? So here's just a practice question. Now, one thing I do want to point out is I have a lot more of these static problems. So if you're having trouble, that's fine. I'm going to go over in a lot more detail in class. It's just more that I want to get the terminology out of the way and kind of go through that. So here's the first question. Pause the video, works up, and we'll go over the second. All right, so let's look at the first question. First question just says, calculate the magnitude of the torques acting on by both these masses. So we have two masses. One is 2 meters away. The other one is 1 meter away. All right. So if I want to figure out what the torque is, I'm going to use this equation. Now I don't need to incorporate the sine theta because the force of gravity that's pulling this down is going directly down, and the angle between that and this pivot arm, which is the radius that it's acting at, is 90 degrees. So I just take the 10 Newton force of gravity and multiply it by the 2 meter pivot arm, and we get that the torque from this left object is 20 Newton meters. All right, I could do the same thing over here. This time, the only real difference is that it's 10 newtons, but same thing applies. I don't have to worry about the angle because the force is straight down, and this pivot arm is directly horizontal, so they're 90 degrees, and we get 10 newton meters. Now the question says, well, what is the net torque acting on the object? Well, again, just like we do in forces, we add the numbers together, but we have to make sure that one of the numbers is positive and one is negative if they're going in opposite directions. So you might think that these objects are going in the same direction because both of these forces are going down. However, that's not going to be the case in terms of torque. And this is important to keep in mind is just because the forces act in a certain direction doesn't mean the torques are acting in that direction. So you can have two objects where the forces are in the same direction and their torques will be in different directions, or they could be acting in the forces can be acting in different directions, but their torques are in the same direction. So you kind of have to think of this separately. So this object, if we imagine that we have a pencil, we put our finger at the very middle of the pencil because that's where the just like the seesaw, that's where it's going to pivot. We apply a downward force on the left hand side. This side is going to lift up, this side is going to lift down, this is going to rotate in a counterclockwise direction. So this is counterclockwise. This object, again, put our finger in the middle of our pencil. We apply a force on the right hand side. Doesn't really matter where. We just apply a force on the right hand side. This side goes down. This side's going to go up. So this would be in a clockwise direction. So this is counterclockwise. This is clockwise. So I have to subtract these two numbers because the torques are in different directions. So I take the 20 and subtract the 10, and I end up getting 10 newton meters, and it's going to be in the counterclockwise direction. Now, like I said before, I know I said, oh, we tend to use counterclockwise as positive. Again, it's whatever. As long as you're being consistent, that's all that really matters. So the net torque would be 10 newton meters in the counterclockwise direction. All right, here's the next one. Pause the video, works up, and we'll go over in a second. All right, so here is a typical rotational equilibrium type question. We have these two masses on this seesaw, and we want to figure out what is the distance that this has to be in order for it to be in equilibrium. So we know that in equilibrium, what that means is that the torque caused by this object and the torque caused by this object have to be equal. Just like how we know that if you have two forces acting on an object and the object's in equilibrium, we know that two forces have to be equal. But this time it's just saying that the two torques are now going to be equal. So I can set the force and distance of this object equal to the force and distance of this object. So 20 times 3 equals 50 times r. Notice I'm not dealing with the angle still because the angle between the forces and the displacement are 90 degrees. So if I solve this for the distance, I get 1.2 meters. All right. Now, one thing to keep in mind is that the boards that we've been using in this problem have been considered massless, right? However, that's not going to always be the case. In fact, it's going to be very common that the object that we're dealing with, the board for the seesaw, might actually have a mass itself. The pivot might be at a different location, not always in the direct middle. So we have to figure out is how do we deal with these type of beams that end up having mass. Now we've talked about before how when you have an object in a system, uh, typically the center of mass is considered where their effective mass is, right? Where if you're dealing with a problem, what you can actually do, like for an object that encompasses three-dimensional space, what you can actually do is just think about all of its mass being placed at its center. And then just imagine the forces acting like that. That's what we're going to do here. We're going to, instead of talking about the mass of this entire long board, we're just going to talk about the mass being located at the center of mass. So we're going to imagine that almost like the entire board is massless, except for that one point where its center of gravity is, where the center of mass is, and that's going to be where all that mass is located. And we also mentioned that all uniform objects will have their center of mass in the direct middle of it. So there you go. If they don't say that it's in, or if the object isn't of uniform mass, they're gonna have to tell you where the mass is. So don't worry about that. In this class, there's no way for you to figure out the mass in any other scenario. So it's either gonna not exist, gonna be where they tell you, or it's going to be at the very center of the object. So that's easy enough. So what you're going to end up doing is having a force acting at that very location, at the very center. Um, Now, one thing to do is that if they don't explicitly say that the board is massless, you do have to make sure that you incorporate the weight of that board. So basically, it's one of those things where if they don't explicitly say that the board's massless, you have to assume that it has mass, and you have to incorporate that. Another thing to keep in mind is that based off that equation, the torque equation, which is Fr sine theta, we know that we get our maximum torque at 90 degrees, but it also means that if we apply a force parallel in the parallel direction, that means we end up, or we apply the force at the pivot, we end up getting zero torque, right? It means that even though we're applying a force, it's not going to be a force that causes the object to rotate. Um, so keep this in mind when you're doing FBD stuff, because or when you're doing these equilibrium problems, because you want to think to yourself is not just like, okay, what are the forces acting on the object, but also, is this force causing the object to rotate? Is it actually providing a torque? And it's really nice when an object when the force doesn't provide torque, because it kind of cleans things up for a bit. And there's actually going to be a lot of cases where there are going to be forces acting on an object that don't actually provide torques to that object. Now, I'm going to go through these steps again in class, but I just want to run through them one time and show you one sample question just so that you have a kind of an idea of it when we go through. But we've talked about the steps that you need to do when dealing with forces. And I tried to make sure in the dynamics unit that I reiterated those steps over and over and over again to try to hammer in the steps you take. We talked about how you usually draw an FBD, you break forces into components, you use your FNet equations, and then you can kind of do other stuff. But those were always like the first three steps. So these are the steps that you have to take when it comes to torques, and it's very similar stuff. Like for example, we do once again start with an FBD. So this is extremely important. It's always this. However, unlike in the force problem where we drew a box and we just kind of drew forces willy-nilly, here what we have to do is we actually do have to draw the object as whatever two-dimensional object it is, like a rectangle or something. And we have to pay attention to the distance or the placement of each force as well as the angles that we're drawing them. So is the force acting perpendicular to it, or is it acting on an angle? We have to incorporate that. The next point, unlike with the forces, we have to locate the pivot. So we have to locate where is the object actually rotating. Now, the really nice thing is that if they don't explicitly mention where the pivot is, or if there is no real pivot, there are actually a few cases where there is no pivot, and the object is in equilibrium, you are allowed to pick a random point. You can pick whatever point you want, and what you can do is you could pick a point that works well for you. Keep in mind that I said it before that any force that acts at the pivot provides no torque. So if you have a problem that is in equilibrium and they don't have an explicit pivot point, you can actually put a pivot, or even if they do, if it does have an actual pivot point, you can pick a pivot wherever you want, but you can pick the pivot point to be at a location that kind of gets rid of a lot of forces that you don't want to deal with, which is really nice. I'll show you an example of that in class because it can be a very useful tool on your end to kind of simplify problems a bit. But what you'd want to do is, a lot of times you're probably going to end up using the pivot that actually exists and that they give you, because there's stuff that does actually act at the pivot that you don't normally know of. All right, so then the third step. Now this, sometimes plays a part, but you have to locate the center of mass of your objects. Like I said, if you have you're doing a seesaw, the board of the seesaw, if it has mass, you have to locate where that center of mass is. All right, and you have to incorporate that as well. So you have to draw the weight coming from the center of mass going straight down. You'll have to draw in and label all the other forces, where they are from their pivots and stuff. And then for each force, what you also want to do is include what direction it is, as far as is it clockwise or counterclockwise? Because what you want to do is you want to have your FBD and you want to be able to just look at the numbers and think to yourself, okay, this is a positive number, this is a negative number, and just kind of throw it down when you're doing this stuff. Sometimes the math can get a little bit tricky, so the whatever you can do to kind of streamline the process will benefit you so much. And this is one of the ways to streamline it is by just having, you know, 20 CCW, 10 CW, 10 CW, 30 CCW, and then just kind of go, okay, that's a positive, that's a negative, negative, positive, you know. And then we would use our torque equations, right? We could do tau equals FR and tau net equals 0 if the object's in equilibrium. All right, so here's the first question that we want to practice on. Pause the video, works up, and we'll go over in a second. All right, so we want to figure out what is the force that this needs to be in order to keep it horizontal. All right, so first thing that I want to do is draw my FBD. We have the center of mass, or we're going to draw it as a full rectangle. So we have the force acting upwards at this point. We have the force of gravity acting downwards at this point, and that force of gravity is 1,000 newtons. At the hinge, there actually is a force acting at the hinge. If you don't believe me, try to lift one end, try to lift one end of the ruler, and you'll know that the other end ends up falling down. So there actually does have to be a force coming from the hinge. This is almost like a normal force acting at this point, pulling this up so that it will actually maintain its balance. Right. So there is three forces acting at this. The pivot we're actually going to put here. The reason being is we're trying to look for this force. We know this force. We don't know anything about this force, and we don't want to know anything about this force. So I'm putting the pivot here so that I don't have to worry about this force, and I can kind of get rid of the torque coming from this. And then what we do is incorporate the distance. So because the beam is 5 meters long, this force has a distance of 5 meters, while this force is 2.5 because it's halfway along the beam. The other thing is that we want to incorporate direction. So this force is going to cause it to rotate clockwise, while this force is going to cause it to rotate counterclockwise. So these are going to be in opposite directions. And this force I don't have to worry about because it's going to provide zero torque. So the torque of the system, the net torque, we know is equal to zero because it's being said that it's going to keep it horizontal, so it's not going to rotate. So that means that these two torques have to be equal, the torque caused by my force and the torque caused by the force of gravity. So I do F times 5 equals 1,000 times 2.5. Again, don't have to worry about the angles because neither of these forces are acting at angles. Solve for F and we get 500 newtons. And that's it. Sorry for a longer video. Like I said, a lot of this stuff I am going to cover a second time in class, a little bit more detail, drawing some images so you can see it. I just want to make sure that I cover this so I don't have to cover the concept of torques in class. All right, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.